your test, I thought what we could try is I want to show you a bit of what actual sort of real life data analysis looks like, because we've done a lot of that. And last year, I know when similar lockdown things were happening, I gave you guys like a really brief overview of the sorts of modeling that goes into analyzing lockdowns and spreads of stuff. And I want to show you now that we know more things like correlation and you've had a go at fitting data to, say, lines of best fit and stuff, I can show you what that actually looks like. And I hope it's interesting for you to see what actual like real life maths might involve. Okay, it's not as clean maybe as what you do in a textbook or whatever, but I hope it's something that might be interesting for you to see. So there's really two parts to this. One part will be something that I hope all of you can actually do yourself by the end of this. Okay, because all it involves is actually quite a simple spreadsheet analysis. Okay, and then we'll talk about the problems with that model, and then we'll talk about how to fix that, and I'll be doing all that live for you. Okay, so I'm going to share a whole screen, I think. Screen 2 is the one. So what I've got up here is the site of data. Now we are also, because of this class, we are missing the current Gladys update. So I'm going to do my own version of that. Okay. So this site tracks pretty much all the info. Oh, it's come out now. It's interesting. Oh, hadn't come out yet when I checked earlier. But this site tracks the live data for everything that we might be interested in. And we might maybe begin with this one, active. So we probably only care about New South Wales, and we will deal with these things a bit later. So let's just download that. I've got a folder, empty folder for you guys here, and that's going to go in as a CSV file here. Okay. Now CSVs are like comma separated, so it's like a text file but put in Excel. So I might actually save this as an Excel file so we can do stuff like make graphs and things like that with it. Okay, I probably don't need to be too concerned with hotel quarantine or these two, so let's just delete these two for now. And when we are doing actual analysis on this, see how this column is full of dates. Right, so this column's only got a bunch of dates there. What I might want to do is actually turn this into a bunch of X values. So we can put a new column there, and we'll just say day number. Maybe we'll start on day 0. And, oh, it still thinks it's a date. We'll fix that afterwards. So we'll just fill that to the bottom first. But now we can turn that to a number, and we can do that. So now we have a column of day numbers. Okay, and so these will be like our X values. These will be like our Y values for the sake of the data analysis. Okay, so we can grab these two columns and try and put a graph to it. Okay, so nothing too fancy. We can just see it's like this. Okay, what sort of graph does that remind you of? If I had to, we've done nonlinear relationships. This is clearly not a straight line, but what sort of nonlinear shape does this remind you of? Exponential, yeah. And we would probably guess that it should be sort of roughly exponential, and that's because, okay, I think when we mentioned last year, we got this far last year. We said that if, say, somebody gets infected, right, they're probably going to infect a good proportion of the people who are close to them. All right. And so it might get maybe, I don't know, 5 out of 6, say, in this dumb model. So maybe it'll get these ones here, right? And then this guy is going to be connected to a bunch of other people. And so is he, and so is he, and so on. And that's why it's not a straight line. It's going to speed up as it goes, right? Because each of these infected people now are going to infect a bunch of other people, right? And so that's going to happen. And so rather than increase by a flat amount every day or something, it's going to probably multiply. It's going to make some sort of percentage increase every single day. And so that's why you'd expect a sort of exponential model to fit, and it sort of is, right? And so when we have something like this, Excel spreadsheets are able to throw trend lines onto things. So let's do that. So this is a straight line one. This would be something you've been doing, right? Using a straight line to fit the data. Obviously, it doesn't fit very well at all. If I try and go exponential, it doesn't like that right now. And I think that's because there's a bunch of zeros here. See these two zeros, right? Exponentials can't hit zero. Remember, I hope that's something you remember from earlier. They don't hit zero when you're depreciating a car or something and it's halving its value every however long. All right, you can keep halving forever, but you'll never hit zero. Yeah, so if you see a zero there, it's not going to like exponentials. So let's just remove these two starting days for now and see. What do we have for this thing? Okay, so now it's letting me go exponential. Okay, so let's do that. All right. That seems like it is way overshooting. If we published this, people would say we were fear-mongering, right? Because it's going way too high, all right? And maybe that's because of the slow start over here. And that's why if you look at the website and stuff, so if you look at the this thing here, when we look at the more recent numbers, you see how it only cares about the last 28 days, because that's when you can sort of see the most recent current pattern. So we can try maybe remove the month of June, say, and see what happens. It's better. It's better. And it may be even just the first half of July or something. We can try remove that. And we're getting something really, really close now. All right. And if we say even only care about the month of August, say, just last month, we get this thing. All right. And that's getting really, really, really close. See how there's a dot here? I think this number just hasn't been updated, this one here. All right. So maybe we'll remove this as well. All right, there we go. That looks like it's a curve fit to the data now. Okay, so what can we do with this? What we care about, I think, is maybe the equation and the r square value. Let me put them up, and we'll make them bigger. We use r squared, not just r, because R, as you know, can be positive or negative depending on whether the line goes uphill or downhill, right? For nonlinear, more general cases, we often just use a square value, but the meaning is the same. Close to 0 means weak or no correlation. Close to 1 means very strong correlation. What do you notice here?
It's almost exactly 1.
It's almost exactly 1, right? And I think in class we'd say this was very, very, like almost too good, right? You also notice the equation has a little e down here, right? I don't think we've mentioned e as much. It's something the other maths classes do. It's a mathematically convenient number, but it's actually a number on your calculator, much like pi is. Okay, so we can even turn this into something we know more by actually calculating what e to the 0.0607 is. So if I just go which is e, exponential, 0.0607, I'm getting 1.06258. Right. When you multiply a number by 1.06, what does that do to it? It's an increase by what percentage?
6%.
6%ish, right? So what we're seeing here is this model is telling us there is something like a 6.26% increase every day. Okay, and that's what the model is telling us. What we'd want to be doing with this is maybe running some sort of forecast, isn't it? Right. So we'd be wanting to maybe use this equation to allow us to substitute other values of x to try and predict what's going to happen, maybe the next few days, the next week, whatever. Okay, so let's try that. The only thing is the x values we're using. See how it's a day number here. So what we need to do is count the number of days since maybe the 15th of June. That's what's going to fit this model here, right? So if we have a oops, date here, I might actually zoom in a bit so hopefully you can see a bit better on the screen. We want to be able to, I might actually make this a bit smaller then, that way. Makes more sense. Okay, so what we want to be able to do is put a date in there, which gives us the day number, which will be like our x value, which we can then sub into the formula to do a predicted value. Okay, So to get the X value, say I want to put a date, maybe tomorrow. Okay, if I put 32/08/2020, oh, well, it's 31 days in August, isn't it? So it'd be the 1st of September, so 01/09/2021. Right, okay. To turn that into a day number, we would want to see how many days has it been since the 15th of June. So we can use a date difference from the 15th of June, so that number there, or that date there, to that date there, and I want to count the number of days. So D should do that for me. Okay, so 78 days. Okay, so that's the X value I'm going to be using and feeding into this equation here. And so all I got to do is copy that equation into here as a formula. So equals 164.16 times exponential 0.0607 times whatever that X value there is. Okay. So we're getting something like this. Okay, so 18684.4 or something for tomorrow. Okay, and so that would be our guess, right? And would this be a good guess right now? It looks like it probably would be right now. Okay, but some people have done similar analysis here, and I've seen it posted on like social media and stuff. And they've said, oh, okay, then, so by Christmas, we're getting 26 million cases a day. I'm like, bro, like, what's wrong? Yeah, it's because of our population, right? There's got to be a limit. There's got to be some sort of ceiling. Okay, so more on that later, but you got to see that there's a limitation to this, right? Even though it looks really good, don't just use the maths and say, oh, the correlation's so big, it's good, right? It's not always the case, yeah, because obviously this is going to stop working quite soon, right? I don't know how soon, okay, and again, we'll look at that in a moment, but clearly this thing is not meant to work forever. Okay, but just for the sake of it, let's run a very similar analysis on maybe the Gladys number. So this number here. So the new ones every day or something. So I think I'm looking for local, aren't I? I'll download that. Okay. That comes up. All right. I guess I'm only interested in New South Wales, so we'll grab these ones. I won't bother saving it because we'll actually reuse a lot of the stuff from our other one. So I might actually make a copy of this, and we'll call this like new or something. And I won't care much for this data. I won't care much for this either. I think what I'll do is grab these dates here, plonk them in there, grab these, plonk them in there. Okay. So everything else should just update for me. Okay. That's what it looks like right now. Okay. What do you notice? Yeah, and I guess that's because the previous one had a lot more data to it, maybe to start with, and so it looked like the span of the previous one was much longer. I think it was going from June, right? And so you could see so much more of the graph. You could see the shape of it and all that stuff. Here we're limited to the month, and so that's why even though the curve is exponential here, you're not going to see it curve as much. It will though. It will. We're just seeing just a tiny little piece of it, so it doesn't look like it's curving that much. What else do you notice about the fit and stuff like that? Might just quickly change this while you're thinking. So it's 214.62. And we are exponential on 0.0647. So it's about 6.5% increase every day we're thinking. All right. And that's our guess for tomorrow, by the way. So it's not fitting as nice, which means we might not think that this number is actually going to be that good. Also, you notice how even though the correlation is really good, you see how the graph is maybe jumping up and down, like the actual data is hopping up and down, sort of above the graph, below the graph, above the graph, below the graph, and so on. Right. And so that would tell us that maybe each individual prediction might not be that good, even if overall it's very good. You see what I mean by that? Yeah, so that's why even though the overall looks really strong here, it is, right? But each predicted value for a particular day might not be that good because it's sort of on average getting that curve, but it's really jumping up and down around it. Okay, and so that's something worth noting, even if the correlations are very nice. Okay, so what can we do with this? How do we deal with that problem of the exponential predicting like 26 million cases a day by Christmas? How do we deal with the weirdness of that maths? Well, there's something we know about those things, something called a logistic curve, and that's something. Have you guys heard of that in biology? No, none of this in bio. No? Oh, okay. Well, it's used a lot in bio to deal with the. Oh, look, it's used to model this. Yeah, to deal with things like carrier transmission, stuff like that. So you see how if I zoom in on the graph of that, it looks real exponential at the beginning, but it's like it knows there's going to be a ceiling. It's going to hit a cap. Right. And so we use this stuff when this thing, I like whether you're modeling herd immunity or vaccinations or just the fact that there's a cap to the number of people in our state, right, means that your exponential won't go forever, but it's going to at some point have to hit some sort of ceiling. Okay, so we use these sorts of curves when that's the case, right? There's also some other maths behind it, but we won't get into that. But that's the general idea of it, okay? And the oops, I probably need that. Sorry. So we're going to actually have to use this equation here. Okay. And you're like, oh, that looks really, really scary. Don't worry though. It's just a calculator thing. Because you're like, what's L, what's K, what's X naught? So I want to explain that first before we get into it. Remember when we were fitting things to lines of best fit? So just straight lines, right? On your calculator, do you remember seeing something like y equals a plus bx? Remember seeing that? Right. What was the meaning of A and B? You should all know this. Yeah. Because we were used to seeing things like y equals the gradient times x plus the y-intercept, right? And so we could see that B corresponded to the gradient and A corresponded to the y-intercept. Yeah. And the whole point of your calculator work, right, when we got into the calculator and we worked out A and B, right, what you did was you put in the x and y values, and the calculator did all the hard work in trying to see which values of A and B best fit the data. Right. And so your calculator's job was to fit the given data to the best, most accurate values of, well, A and B. Okay, and it was simple that way because a straight lines equation only has two numbers, gradient and y-intercepts, right? We have, I guess, three numbers. We have an L, we have a K, we have an X naught. Okay, but it's the same idea, isn't it? You don't have to know, like, you don't have to be scared of this because the computer's going to do it. Just like how your calculator did all the hard work for you. All we need to know is there are three numbers, L, K, and X naught, just like in the calculator, there were two numbers, A and B. Okay, so we're going to do the same thing. And if we actually look back, sorry, I keep doing this. If we look back at what those things represent, we might need that in a sec to think about what's going on. So these three numbers. So K is a steepness, a bit like gradient maybe. L is the max value, that ceiling it hits is the L. And X naught is the middle of the sort of inflection point, we say. Okay, that sort of turning point there. All right. And so we need a calculator that can do this, that can sort of do the thing that your calculator's been doing all this time. And the best way I know, because Excel can't do it, or not easily anyway, is to use a Python file. So let me just run that. This is where we get like full geek, but don't worry too much if you don't understand what I'm doing here. I just want you to see what the process is and to see the pictures that come out as a result of this. Hopefully that's somewhat interesting to you. All right, so let's not worry about this is my animation stuff, but I'm going to need the curve fit from this thing. I'm going to need a curve fitting thing. I am going to need numbers, and I am going to need a thing to plot a graph. I'm going to need to feed this thing all the data, so let's do that first. It's a list of numbers, and I'm going to give it, let's do the local first. Let's give it all these numbers here. Yeah, that will do. Put all these numbers there. It's a list of numbers, so I need commas on everything. It's just a coding thing. So I'm going to put commas on all that. That. Great. Okay, so that's my numbers. All right. I need x values. X values are easy though. X values are just a range of numbers from 0, 1, 2, 3, all the way up. So let's just do that. So a range of numbers from 0 to however long my y data set is. Okay, and even that by itself is probably enough to show you a bit of a plot. I can plot all the x values or the y values as a solid blue line, and the label will be the actual data. So I'll put that there. I want a legend, and we want to show, and this is what it gives me. Okay, so it looks really similar, I think, to the thing we had over here. It's got to be the same, right? So that's the way we're going to plot this, so we can use some higher power tools to do it now. Okay, so that's what I've got so far. I now need to put in that ooh, why is my face gone funny? Oh, because I use the same hotkey to run the program. Oh, sorry, my face is going to go in and out through the whole thing. I need to now put in this formula here. Okay, so let me just run that real quick. I need logistic. It takes an x value, takes the L, takes the K, takes the x naught. And what it gives me is L over 1 plus the exponential again, negative K times x minus x naught. Okay, and that's all it's going to do. So that's the equation there. Remember, I might just take note of this. L from the Wikipedia article. L was the ceiling, right? So L is ceiling. K is some sort of gradient, maybe, and x naught is the center, whatever that might be. Okay, so that's the meaning of those three numbers. Okay, so now it's the computer's going to do all the calculation for me. All I need to give it though is a guess. So the computer can do it for me, but I need to give it a first guess from which it can do little tweaks and try and work out the best one. So maybe the guess I will give it is that the ceiling, maybe I'll just feed it the maximum value so far. So the max of all the y values. The gradient, I'll just say, I don't know, maybe half. And the center, I'll be optimistic and say that we're close to turning. So I'll give it the max of all the x values as well and see what happens. Okay. All right, that's my guess. Now the computer can do the fit for me. So my parameters optimized will be the curve fits. I want to fit a logistic curve, the thing I defined above, to the x values and the y values, and I will give it my guess as well. And this just makes it work properly. Okay, and that's all I need to put in for the computer to do the calculation for me. Okay, so I'm going to do another plot where we do the x values, and rather than just plot the y values, I'll put my fitted curve in. So I want to put a logistic curve on the x values, giving it the optimized data, optimized parameters, and we'll make this a red line dashed, and we'll label it fit and see what happens. Okay, get this. It looks the same, doesn't it? Right? It looks pretty much the same as the thing we had before, and that's because maybe this fit it hasn't turned yet. It hasn't reached the point where it's going to turn, and that's expected because the exponential sort of fits really well, which means we're probably still around here in the development of all this. You know how in the news they keep saying expected to get worse, right? Expected to get worse. That's probably because we're still here. So we're still going to climb a little bit probably before turning. Now, I don't know for sure because the whole point of this is we are only in these really, really early days here. And so we're not quite there yet. All right. So maybe what we want to do is two things. Our goals will be to forecast this, see where it's going, right? Because again, this is really small in terms of the scope. So I want to see where it's going, and then maybe also run a correlation or something. Okay, so let's try and see where it's going first. Let's try and forecast this. To do that, I probably just need more x values, don't I? So I'll copy this, and let's forecast, say, 100 days ahead. So plus 100 to all the x value range. And I don't want to mess with the calculation. I will call this the forecast X data, but I want to plot this plot here, the fitted curve. I want to plot that going ahead. And I get this. All right. It's rather interesting. Don't think I've heard this before. This day actually made it quite different. It's rather interesting. Okay. So sorry.
Is this saying the max cases will be 3,000 a day?
Well, currently, like that's what it's saying right now, right? That's what the math says. Can we trust it? That's a good question. Like, I almost want to hear what you think. Like, can we trust this? Because I'm not a biologist. I don't or what do you call the epidemiologist? I'm not those guys. So can you trust this? Well, probably not until we know we've hit that point where it turns. That's what I'm guessing. Because the fact that it still looks exponential right now is a little bit like this thing. Like, it's sort of like we know that it's going to do this eventually because there's a capped number of people. But is this the best model right now given our current data? Probably not yet, because it's still too early, right? If I make myself a bit less optimistic and I make this maybe the median rather than the max, I wonder if that changes much. And it doesn't change all too much. It's still doing that. But yeah, it's interesting to see. I'd want to track it probably until we're convinced we've reached that point where it's going to turn, right? So I reckon this is probably not reliable until we see a bit of a turn. Once it starts turning a little bit, then we can sort of map it on and see where it's going to end.
By turning, do you mean like case numbers start flattening out?
Yeah, I mean this point here.
Okay.
Yeah, you see how it's sort of going up and then it's going to eventually hit some sort of breaking point where it's going to have to slow down again because either everyone's got it or like vaccinations happen or whatever, right? So it's going to have to reach a point like this for whatever reason. And until we sort of clearly, I think, reach that point, any modeling we do probably isn't going to be all too accurate. Right, no matter how big the R square is, and I might try that now just to see. I don't know what the R square will be here. I don't think this has a sort of built-in function for that. We need to manually work out the errors and stuff. So my errors will be the y data minus my fit on the x data with the parameters put in. Sum of squares will be the sum of the squares there, and my actual variance of the data will be the, I guess, sum of the y data minus the mean of the y values, I think. Yeah. Let me square that. Okay, so I'm comparing the difference between the fitted curve and the actual data. I'm comparing that with the variance of the actual data, and that's actually where correlation comes from. So the R square value will be 1 minus the comparison between the two. So I'll put a fake plot to show it. So nothing white, but my label will be the R square value. Format R square. Okay. Let's see what that fit is going to look like. Being like 0.964, right? So that's pretty good still, but only mathematically good. Again, there's a difference between, again, maths and real life, and when we look at this from a real life perspective, we're like, we still haven't reached that point where we can conclude that this is happening. So what I would do if I was really interested in this is I'd keep this code here, right, and I would sort of run it over and over again as the days progress to sort of track this as this thing hopefully begins to flatten soon. That's, I think, what I'd be doing with it for real. Okay, and if I was more fancy, I'd write another piece of code that would read the website and automatically filter the data in as possible. And this graph could be sort of built over the next few days, right? So yeah, I think that's what it's like. We need to know what we can conclude, what we can't conclude, right? And we know what models are good, which models sort of work. But even then, even fitting a good model to this, when you look at the shape of where the data is taking us right now and where we're going, we still see there's a fair bit of uncertainty there, just because of where we are, right? So hopefully, actually, over the next week or so, if we do more of this, right, then we can maybe see where we're going. I reckon. I think that's pretty cool. For fun, we could even go back on this one, and is this Thursday's lesson? No, let's go for second of September. Thursday's lesson, I'm guessing it might be something like this. All right, I'll put that in here as well, and we can see how close we are, just for the sake of it. That's the total though, so that's why the number's high. And like, I'm actually hoping we're a bit wrong, because the Excel one is the pure exponential. So the more wrong this gets, I would say the better shape we're in. Okay, because we want this thing to start being wrong as soon as possible, right? Because this is the curve that just keeps going forever, right? If we had to forecast like this one, it'd be going pretty crazy. I think it'd be shooting up to who knows where. So this is the one we sort of want to be wrong as soon as possible, because we want to switch from this model to this one here. All right, and so that's what we're hoping for. What we're hoping for is that this one gets more and more inaccurate, and then we can get more data to feed into this one, and then we can make a pretty good sort of estimate for where it's going to flatten and how it's going to develop from there. Okay. Any questions on that?
How long have you been using spreadsheets, sir?
I don't use spreadsheets very much. I'm not very good with these.
You seem pretty good with it.
No. Like actual data analysts and people who work in corporate, like they'll be using things like pivot tables and stuff. I don't know about that. I know basic spreadsheets and I know this stuff. I don't know any in between. So I sort of like, I can do it, but it's probably like, is this necessary? As far as I know, yes, but maybe there's a way to get into the spreadsheet and make it do this as well. I don't know those things, so I just use this. Shouldn't it decline as we get closer to 7? Yeah. Well, that's the thing. Like, the herd immunity equation is one that we can't actually use in this course. It uses calculus and stuff, and the other courses have. It's a differential equation, and we think that the model here is actually taking that into account. The fact that it's going to slow down and go, because the vaccinations don't fully stop all sort of transmission and stuff like that, right? But it's going to help us slow it down and cap it somewhere, and seeing how the data develops will hopefully lead us to a pretty accurate cap. But I don't know. I'm curious as well. Yeah, exactly. So whether it's herd immunity or vaccinations or whatever it is, or a combination of everything, it's going to start dropping at some point, but it's probably going to reach something like this. A full equation might make this go up, then flatten, and then come back down in terms of new cases and stuff. All right, but we won't look into that one. It's maybe even a bit more like a bell curve sort of shape, not the same, but similar. Anything else? So maybe even on Thursday next week, we might check back in on this and just see what's happening. I won't go through all the details. I'll keep this saved so that we can just like add the extra numbers to this as the days go by, and hopefully that's going to be something we can see for the fun of it, I think.
So
yeah,
do you reckon your prediction is going to be close to right?
If you're saying like the next day, probably not. Like, so say my thing for Thursday, like this is our Thursday prediction, isn't it? All right.
Mm-hmm.
Probably not, just because of, again, how the graph is jumping up and down through the line. What we're predicting is on the dotted line, right?
Mm-hmm.
And so it's depending on how it's going to jump like up and down and stuff like that. Or maybe if we're like really wrong because we have hit that tipping point, that'd be good. Like, I'd be really happy about being wrong if it's that, right? So it all depends on what's happening. Like, that's why real life is never such a clean game like maths is. You can predict anything in maths. Like, you just put an equation and you're like, oh, sweet, right? But real life, it's jumping C, right? So like the comedian who's getting it all right, like all the time, like it's just a joke, right? Because this is what it looks like in real life, right? Mm-hmm. You have your fit, you have your data, and it's as good as this is really, really, really good, right? But it's still going to be jumping up and down through the line, and there'll be little differences. You will never be perfect to the number. Okay. So yeah, I'm hoping to be wrong for a bigger reason than just variance. But we'll have to see, really. We'll have to see.
Yes.